Good. Okay, go ahead. All right. Good morning, everyone. I'm Sanjeev. I'm a master's student in material science and engineering. I work with Dr. Dev Chidambaram, and most of my lab mates are sitting right here. My current research work is in the electrodeposition of terbium in molten salts. Now, terbium is, most of you probably did not hear about terbium. So it's the first member of the heavy rare earth elements with the atomic number 65. It's a silvery white metal. It's a silvery white metal which is malleable, ductile, and is soft enough to be cut with a knife. Now, why these elements actually got the name rare earth is a bit weird. Like, when they were discovered a couple of years back, it was really difficult to actually separate these elements from their ores. So they were rarely used for anything, so they got the term rare earths. Now, probably the most, why are we actually investigating terbium? The most common use of terbium right now is in phosphors. Phosphor is any material which emits light when struck by electrons. So you have phosphors in fluorescent lamps and bulbs, in television tubes, and terbium phosphors are specifically green light emitters. So they're used in TV tubes and phosphorescent lamps. Now, terbium is also alloyed with different elements, with different rare earth elements and other magnetic elements to exploit some of it, to better exploit some of its uses. It's alloyed with iron and another rare earth element, which is dysprosium, to form the magnetostrictive material terphenol D. Terphenol D is basic. Magnetostrictive materials are basically those materials which expand or contract in external applied magnetic fields. So when you actually apply a magnetic field to them, the output you get from them is mechanical, or like the piezoelectric materials, but they're just better. And and magnetostrictive materials they have a very high frequency. And terphenol D, when you use it, it's a device which you can stick onto any surface like glass or solid walls, and with the vibration it gives out, it'll actually vibrate the entire surface, producing vibrations and producing sound. So if actually in a store, if people stuck it on the glass window, it would actually vibrate the entire thing, producing sound. So that's pretty amazing applications. And earlier I told you that I'm investigating molten salts. So molten salts are basically salts which are solid at room temperatures, but when raised to elevated temperatures, they melt, and they're very good ionic conductors. The molten salts I'm using are eutectic composition of lithium chloride, potassium chloride, and the temperature ranges are about 450 to 600 degrees Celsius. Now, terbium, basically what I'm trying to achieve is electrodeposit the terbium from its chloride form onto my cathode, which incidentally I'm using tungsten or stainless steel. And the anodes I'm using are graphite. Presently I'm just using a 2 electrode setup, and once I achieve the electrodeposition, plan to move on to more intensive electrochemical testing like cyclic voltammetry, etc. I don't want to go into details of that. And I guess I'm done. Thank you. Not even 4 minutes? Okay, I could actually. I had a bunch more. Well, it's only 4 minutes?
That's 4 minutes.
Wow. Okay.
Yeah,
I
fine.
think
you can keep going.
Again?
You have 30 seconds left.
Oh, okay. Yeah, molten salts are actually molten salts are actually being intensively investigated recently, mostly because, like my friend Gus talked about in his last talk, pyroprocessing of nuclear fuel, reprocessing of uranium and plutonium for their reuse. So molten salts are primarily the most sought after media for any kind of electrochemical testing, like electrorefining, electroreduction, or electrodeposition of the metals. Thank you. Okay, any questions?
Where do you plan to get your supply of terbium chloride? Why do you start that?
Why do we start terbium chloride? Okay, so right now terbium, these rare earth metals existing in their elemental form, it's really tough. They usually don't. They generally just oxidize. You need special environments to keep them in their elemental form. So the extraction process we have right now, it has been developed until the rare earth elements from their ores are selectively separated out into their chloride forms. So that is kind of where we're starting off from. Okay. All right. Thank you.